All right, so we're going to start off drawing CH2O. This one's going to be a little bit harder. So if this is an organic compound, how do I know? A main component of an organic compound is carbons, and then when you see hydrogens and oxygens, it's almost always, well, it is an organic compound. So like carbon with hydrogens and oxygens are called organic compounds. And if you remember from yesterday, I told you if you see what element in a compound, it's almost always in the middle. Does anybody remember who that is? Okay, so the answer is carbon. So I'm going to kind of set this up for you. I'm going to do this right here. And again, you wouldn't know how to do this yet. I'm just organizing where the each element is going to go. And now I would like you to fill in every single element's valence electrons. So that's what you're going to do first, always. So I organized it for you. So carbon has 1, 2, 3, 4 valence electrons, right? Hydrogen has 1. Hydrogen has 1. Oxygen has 6. So 1, 2, 3, 4. Now see how it's lined up here? So I know I'm gonna have to bond this, so I'm not gonna pair this guy up yet. So I'm gonna kind of go back here and do 5, 6. All right, now in order to draw structures, we have to link them. Like everything has to be linked or it won't work. Now someone's gonna go, well, why can't I just link hydrogen and hydrogen? Well, because then if you link hydrogen and hydrogen, then these can't bond to the compound. Remember, and if you don't remember, write this down. Hydrogen can only bond one time. That's it. Ever, 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 ever. It can only bond once. So if you bonded the 2 hydrogens, you wouldn't be able to bond the rest of the compound. So it would be over. So let's see. How about carbon to hydrogen? There's 1 bond. Was a single covalent bond. See, what else can I do? Well, carbon to hydrogen, right? Okay, so now the hydrogen's bonded, this hydrogen's bonded, but I see I have a loner electron here and a lone electron here. This is not a lone pair, it's an electron that's not paired up. So I'm gonna do that. Now we have an issue, and the issue is that nothing is stable. Well, the hydrogen.
Ms. Murphy?
Yep.
I don't see it.
Oh, sorry. Okay, so I did my 4 electrons around here, my 1 electron to each hydrogen, and my 6 to the oxygen. And then I started linking them up, okay? Now, what's happened is the hydrogen is stable, it has 1, 2 electrons. This hydrogen is stable, it has 1, 2 electrons. The carbon has 2, 4, 6, 7. How many valence electrons does carbon want to have to be stable? What's the magic number for carbon and most other elements? 8, right? The word octet means 8. That's what most elements want to have to be stable. So what I am forced to do, and see, look at the oxygen isn't stable either. 1, 2, 3, 4, 5, 6, 7. I'm forced to form a multiple bond. This is called a double covalent bond. 2 lines means double, so there's 4 electrons involved in this bond instead of 2. Now, this is kind of ugly, which most of your Lewis structures will be when you start drawing them. So I'm just going to redraw it nicely, okay? I'm just going to redo this so that it looks a little bit cleaner. So it's bonded to a hydrogen, it's bonded to another hydrogen, and then there's what's known as a double bond to the oxygen. You have to include the lone pairs. If you do not, you will get marked off wrong. So now look at carbon has 2, 4, 6, 8 electrons around it. Okay, what about oxygen? Oxygen has 2, 4, 6, 8 electrons around it. So it's achieved an octet of electrons. Oops. Okay. Hydrogen only has 2 around it. It's a duet, but remember that is what hydrogen is most stable like. Or that's the only thing it can't do. Hydrogen can only bond 1 time. Okay, and same with this hydrogen. 2 electrons sharing with this hydrogen. So now we've introduced double bonds. So this is called a double bond. So this is a single covalent bond. This is a single covalent bond. This is a double covalent bond. Double covalent bonds are stronger than single covalent bonds, meaning they're harder to break. Okay? So let's see. Let me go to. So again, I've drawn it right here. I don't need you to know this part right here. This bond is actually called a sigma and a pi bond, but we're just going to call it a double bond. So again, there's 4 electrons total involved in a double bond. This guy's chemical name is formaldehyde. If you don't know, formaldehyde is what they used to like preserve and preserve things like bodies and such. They don't use it anymore because it's considered carcinogenic. But this is the chemical structure for formaldehyde. Okay. So now I want to practice drawing O2. So let's see. O2. This is diatomic, right? So I draw an oxygen and an oxygen. 2 oxygens. All right, so let's get good at this. How many valence electrons does oxygen have? I'm not going to be checking the chat, so if you could shout out, that would be great. So you go to your periodic table. It has how many valence electrons?
6.
Thank you. 1, 2, 3, 4, 5. Now, I know I'm going to probably end up bonding here, so I'm going to draw my second one here, 6. Okay? And then this oxygen also has 6. 1, 2, 3, 4, 5, 6. All right, I would like you to try to finish this. I want to see how you would do this. You try to hook them up. You have to bond everything at least one time or it won't work. So look, there's an electron by itself, an electron by itself. Bond. Any suggestions for the next step? Suggestions? So look at, we're going to hook up this lone electron and this lone electron. So I'm going to redraw this because it's kind of ugly. A double bond. And then you have to include all lone pairs that are left over or you will get docked points. Okay? So look at, let's count the electrons. 2, 4, 6, 8 electrons for this oxygen. It has now achieved an octet. Let's look at this guy. 1, 2, 3, I'm sorry, 2, 4, 6, 8. 8 electrons. It has achieved an octet, which is stable. All right, so here it is. All right, we're going to draw C2H2. Now I'm going to kind of, organic molecules are interesting. Remember, we always said carbons are in the middle, okay? And then I'm going to, oops, I didn't want to do that in pink. I'm just going to show you that the hydrogens are right here, okay? So first thing you do, 1, 2, 3, 4, because carbon has 4 valence electrons. 1, 2, 3, 4. All right, how many valence electrons does hydrogen have? 1. Hydrogen has 1. How many times can hydrogen bond? 1 time. That's it. So the hydrogen is taken care of. Any suggestions, I'm going to give you a chance to finish, of what this might look like? So I have to at least hook the carbons up once. Have we achieved stability yet? No. So maybe this one and this one I can put together as another bond, and maybe this one and this one. So this is 3 lines, which is known as a triple bond. This guy's name is called ethine. Okay, so it's called a triple bond. It is the strongest of the 3 covalent bonds. So single, double, triple. Triple is the strongest. There is no such thing as a quadruple bond. So this is as strong as it gets. Triple bonds are the hardest to break. Think about like karate chopping. If you had to karate chop through 1 piece of wood as opposed to 3 pieces of wood, right? Karate chop means like breaking. It's easier to break 1 piece of wood than it is to chop through 3 pieces of wood. Okay, so this is the strongest type of bond, a triple bond. Okay, so 2, 4, 6 electrons shared in a triple bond. All right. So there are some exceptions to the octet rule. Like, right, we said hydrogen is stable, bonding only once, and in fact that's how it is stable. It won't bond more than 1 time. And so there's going to be a couple of exceptions that we're going to have to learn. So beryllium, so if we go to our periodic table, okay, beryllium is right here. It has 2 valence electrons, okay? And it is really, really small. It's a fairly small element. And because of that, it's 2 valence electrons. So if you were to draw beryllium, like 1, 2 valence electrons, it is okay only bonding twice. Now, if it only bonds twice, it only ends up with 4 electrons around it, not 8. And that is okay. Beryllium is okay like that. It is stable like that. Now, that doesn't mean it can't form more than 1 bond and up to 8 electrons. It just means it's generally more stable, only forming 2 bonds with a total of 4 electrons. So they call this an incomplete octet because an octet would be 8. So if you have less than 8, which is 4, you don't have as many electrons as the octet rule requires. So then let's look at another exception, boron. So boron is considered to have an incomplete octet. So if we go over here, boron is right here. So right, this is 1 valence electron, 2, 3, 4, 5, 6, 7, 8, and then this, except for helium, okay? So boron has 3 valence electrons, right? So 1, 2, 3. So it is okay bonding only 3 times. Now, if it bonds only 3 times, 2 electrons, 4, 6. It will only have 6 electrons around it, not 8. It is okay and it is stable this way. It has an incomplete octet because it's a small atom and it can be stable with 6 electrons. That doesn't mean it can't have 8 valence electrons around it or 8 electrons being shared around it. It's just okay and still stable with only 6. So these are 2 exceptions that you need to, some of the exceptions that you need to know. Okay, so just like you can have an incomplete octet, you can also have what's called an expanded octet, and we're going to talk about this in just a little bit more detail in just a second. So expanded means you can have more than 8 electrons around your central atom. So these are 2 examples I'm giving. These are not the only 2. There are many, many more that can do this. Pretty much, hold on, where's my periodic table? Pretty much everybody from the 3rd period on, and now I'm going to focus on like these guys. Okay, the reason I'm not focusing on I should delete that. So anybody from the 3rd period on, and again, I tend to be focusing over here because these guys are metals, and metals don't tend to form covalent bonds, and that's what we're talking about. Remember, we're talking about mostly nonmetals. So let's talk about why. Why can like phosphor and sulfurous do this? Well, let's do the electron configuration for phosphorus and let's do it for sulfur. We'll do noble gas notation. So phosphorus is neon, 3s2, 1, 2, 3, 3p3. Okay, and sulfur is neon, 3s2, 3p4. Okay, so you go, okay, well, on the third energy level, on n equals 3, the third energy level, which types of orbitals are there? Are there s orbitals? Yes. Are there p orbitals? Yes, this is 3p, right? Are there d orbitals? What are these called? What d is this? 3d. Okay, so there are d orbitals, but the thing is, they haven't been filled in yet, so they're empty, which means we have another location on my third energy level where we can throw extra electrons into. So the reason I can do this from the third energy level on is because 3d is where the d orbitals are. You cannot do this with any second energy level elements because they don't, I hate when that happens, because they don't have d orbitals. There's no such thing, so none of these guys can do that. There's no such thing as 2d, and if there's no such thing as 2d, there's not empty d orbitals to throw elements into, or electrons into. So again, these guys from the third period on, okay, can have expanded octets because they have empty d orbitals that we haven't reached yet. So you go, okay, well, what about arsenic? If I do arsenic, I filled in the 3d, so where would extra electrons go? Well, that's a great question. So let's do the noble gas notation for arsenic. Noble gas notation for arsenic. So arsenic. Okay, it's in the same family as phosphorus. I said phosphorus can do it, which means arsenic should be able to do it, right? So like these guys. Okay, so let's do it. So it's argon, right? 4s2, 3d10, 4s2, 3d10, 4p3. And you go, but the d orbitals are filled in. The highest occupied energy level for arsenic is energy level 4. Are there such thing as 4 d orbitals? Yes. Have we hit them yet? No. So they're not full. They are empty. So the d orbitals are also empty for arsenic and so on. Okay, so this allows what are known as expanded octets. So let's draw sulfur. Sulfur has 1, 2, 3, 4, 5, 6. Sulfur likes to bond twice. Okay, that's a common thing for it. But it is also okay splitting up the lone pairs and bonding all 6 times. It is able to do that. Now, when it does that, it has 2, 4, 6, 8, 10, 12 electrons around it. That's an expanded octet. It's more than 8 electrons around it, and it is stable like this. Okay? Phosphorus has 5 valence electrons. So you go, okay, phosphorus. 1, 2, 3, 4, 5. Now, phosphorus, you'll often see do this and form 3 covalent bonds, but it has the potential to split up that lone pair and form 5 bonds. That would give it 2, 4, 6, 8, 10 electrons around it, which is an expanded octet, and it's stable this way. All right? Any questions so far? So we're going to kind of go from here. So let's talk about bonds and multiple bonds. Sorry, that's kind of hard to read, huh? Bond dissociation. So dissociation means to break. So bond dissociation energy, so the energy required to break a bond goes as such. Single bonds are the easiest to break, so they have the lowest bond dissociation energy. You don't have to put in a lot of energy to break them. And then double are a little harder to break, and then triple are the hardest to break. So low bond dissociation energy is a single bond, and the highest bond dissociation energy is a triple bond. If something has high bond dissociation energy, it means it's very difficult to break that bond. Okay? Now, here is why. Because there are more electrons involved in a double bond, there is more attraction between these two atoms. So they're closer together. What do we know about things that are closer together? They're held more tightly and therefore harder to break. A triple bond is the shortest. Okay, it's the shortest bond. So the distance between this nitrogen and this nitrogen is really small relative to any of these other bonds with the exception of this guy right here. Okay, so because they're short, the two atoms are really close together. If the two atoms are really close together, these electrons right here experience a really strong attraction to each of these guys' nuclei, I should say. And if they are really attracted to each other, to try to rip through them and break them apart is going to be very difficult. So smaller bond length is associated with higher bond dissociation energy or higher bond energy. Okay? So there's two things that's going to affect the bond dissociation energy. So right now what we're doing is bond dissociation energy, and this is going to be for covalent bonds because everything we're drawing right now is for covalent bonds. So what does covalent mean? These are nonmetals with other nonmetals. Okay? We'll talk about lattice energy next. We're not there yet. So which of the following bond pairs has the higher bond dissociation energy? So when you see that, you see higher bond dissociation energy, you need to think to yourself, harder to break apart. Harder to break apart. So now chlorine and iodine. Now I'm going to draw them. Chlorine has 7 valence electrons, right? So here's chlorine. Now I'm going to do iodine. Iodine also has 7 valence electrons. These are both halogens. 1, 2, 3, 4, 5, 6, 7. Iodine. 1, 2, 3, 4, 5, 6, 7. Sorry, that's kind of ugly. Oops, I should have. Okay. Single bond, single bond. So if the bond types are the same, what plays a role is the size of the atom, because single bonds are the easiest to break. So if they're both single bonds, then you go, well, how do I pick? Well, this is the relative radius for chlorine, and this is the relative radius for iodine. The closer they are together, the harder the bond is to break. So chlorine will have the highest bond dissociation energy because the atoms are smaller and therefore closer together, which makes them harder to rip apart. Okay, so again, when the bond is the same type of bond, this is a single bond, this is a single bond, it's size that plays the role. Okay, now nitrogen or O2. So now I would like you to take a moment and I would like you to draw nitrogen and then I'd like you to draw O2. So you guys take your time to do that, please. Oops, I'll set them up for you. I'm going to have to draw it up here, sorry. Nitrogen has 5 valence electrons. Okay, and then oxygen is over here. It has 6 valence electrons. So let's see. I've got to connect them at least once. And then I still haven't achieved stability, so I'm going to connect again. Okay, this is stable. I'll redraw. It looks like this. Okay, what about N2? So I definitely have to connect them at least once. I have not achieved an octet yet, so I'm not stable yet. So I'm just finding all my electrons that are by themselves and pairing them. Look at, there's still a lone electron and a lone electron. Okay, this is ugly, but there are 3 lines between it. So I'm going to redraw it with 3 lines in between it. And then the lone pair is still there. So which one has a higher bond dissociation energy and why? Which one is harder to break apart and why? Anybody? So you should pick N2. And why? Because it has a triple bond. And triple bond is a short bond, which means these guys are closer together. And if they're closer together, they're harder to rip apart. So the size of the atom wasn't relevant for this one. Instantly, triple bonds have way higher bond dissociation energy than double bonds. Okay? So now, for ionic compounds, which we haven't been talking all that much about so far, we'll talk a little bit more about them today. Remember, ionic compounds generally involve metals with nonmetals. So if you look on our periodic table, that's going to be like, oops, metals pairing up with nonmetals. So these guys with these guys. Before we were just focusing over here with things over here. So the reason that this happens for ionic compounds is a transfer of electrons, okay? One thing loses them and the other thing gains them. There's no sharing involved. No sharing in ionic compounds. So in ionic compounds, the thing that holds them together, so we have bond energy that holds covalent bonds together. The thing that holds ionic compounds together is known as lattice energy, okay? Lattice energy is specific to ionic compounds. That means metals with nonmetals or metals with polyatomic ions, okay? I'll give you an example of negative lattice energies later, but the more negative the lattice energy, the stronger the force of attraction. So what holds them together is charge. Oops. The positive and negative attraction is what holds ionic bonds together, okay? So there's 2 ways to look at this. All right. So ionic compounds have actual charges, right? This is called an electrostatic force, where if something loses an electron, it becomes positively charged. And if something gains an electron, it becomes negatively charged. And the positive and negative attract each other. And that's what holds the ionic compound together, this lattice energy, this electrostatic force. So for the things that have the same charge, things that have the same charge. So my charges are kind of messed up, but if you look at the periodic table, let's go back to common ions. So we need to rediscuss valence electrons. What are our common ions? Now, common ions are used for ionic compounds only. So, right, your alkali metal family likes to be +1. Why? They have 1 valence electron, they would like to get rid of it. Your alkaline earth metal family tends to be +2. Why? They have 2 valence electrons, they'd like to get rid of them. Your boron family is +3. Why? They have 3 valence electrons, they'd like to get rid of them. Now, this is where it gets different. The carbon family is ±4. Meaning it can just as easily lose 4 as it can gain 4. Now here's where nitrogen gets funky. What is this nitrogen family? Well, the nitrogen family has 5 valence electrons. So it has 2 options. It can lose 5 and go backwards 1, 2, 3, 4, 5, or it can gain 1, 2, 3. What do you think is less work? Well, gaining 3 is easier than losing 5. So if you gain 3 electrons, this whole family is going to be minus 3. So guess what this family is? This family has 6 valence electrons, oxygen family. So it can either lose 6 or gain 1, 2. Well, it's much easier to gain 2 than it is to lose 6. Oops. So gaining 2 would make this minus 2. Then this family is minus 1. And then this family is going to be no charge, right? Your noble gases don't want to gain or lose electrons. So these are our common ions for every single family on here. Okay? Now, charge plays the role. So the first thing I have on here is potassium chloride. So, oops, okay, potassium chloride and lithium chloride. So I'm going to go back here. I'm going to write here. If you look on your periodic table, potassium is +1 and chlorine is -1. Now lithium is also +1 and chlorine is -1. So let's look back on my periodic table just to make sure I did that right. So potassium +1, chlorine -1. Perfect. Lithium +1, chlorine -1. So they're the same amount of charge, which means charge is not going to be the factor. The factor is going to be the size again. Chlorine is the same in both of them. So it's not going to be chlorine. Well, this is technically called chloride, okay? But lithium is a smaller cation than potassium. So this is radius, right? Look at lithium is up here, has 2 rings of electrons. Potassium has 4. So if lithium is smaller, that means this is held together, this attraction is held together more tightly, and it has a higher lattice energy, the largest lattice energy. Now, lattice energies are negative, so this kind of confuses kids. But this would be a harder compound to rip apart than this one because the ions are closer together based on size. So the size is playing a part. Now, because we're talking about ions and ions have charge meaning positive, negative, charge also plays a role. So again, this is kind of funky. So look, magnesium is a +2 cation, oxygen is a -2 cation. Lithium is a +1 cation, oxygen or chloride is a -1 anion. Sorry, this is an anion, oxygen. Okay, +2 -2, +1 -1. Okay, so I'm going to go back to my periodic table and just make sure we did this right. Make sure magnesium is a +2. Magnesium is a +2. Oxygen is a -2. Okay, +2 -2. Lithium is a +1. Chlorine is a -1. So the one that has a higher lattice energy, the more negative lattice energy, is going to be this guy. This guy is harder to break apart. Charge trumps size. Charge trumps size, meaning the more charge you have, the stronger the lattice energy. So if you had to pick between the two, charge will always beat size, meaning this ionic compound is actually smaller, but it's only made up of a +1 and a -1. This is a little bit bigger, but the +2 and -2 is a way stronger force of attraction, so the charge will always play a bigger role than the size. Now, that didn't happen in the last one because they were both the same charge, +1, -1, +1, -1. So we didn't have to consider charge over here. We had to consider size. The second you see different charges, the higher charges, instantly has the larger lattice energy. So, remember, for bonding, by forming bonds, so this is sharing, atoms acquire an octet or duet of electrons. So this is covalent bonds, okay? By sharing. That's one way. In an ionic bond, the metal, usually metals and non-metals, happen because one thing loses the electron and the other thing will gain it. That will give each of them now an octet. It's still an octet of electrons, it's just octet using a different route. So in covalent bonds, the issue is that neither one of the elements is strong enough to completely rip the electrons away from the other one, so they're forced to share them. All right? Ionic bonds are the opposite. In an ionic bond, usually you have a metal, which metals tend to want to lose electrons, and the nonmetals really want to gain them. So the one thing's like, cool, you can take mine, and the other thing's like, great, I will. And then they're both happy with that, that arrangement. Why is this doing that? Okay, we are going to end with this. I'm going to do the basic ones. This valence shell electron pair repulsion theory is based on, these are going to determine our shapes, okay? Our shapes, called molecular shapes, meaning if you can't draw Lewis structures, you can't do this, all right? Valence shell electron pair repulsion theory. So VSEPR is how they abbreviate it. And it's the idea that the valence shell electrons on the central atom are responsible for causing different shapes. So here's what I'm going to mean. Let's draw carbon dioxide. So first guess, who's in the middle? Carbon or oxygen?
Carbon.
Good, carbon, right? I told you it's almost always in the middle if you see it in a compound, carbon. Then I'm going to put my two oxygens on each side of it, okay? So carbon is my central atom. Now fill in all of your electrons. Carbon has 4, it can donate. Oxygen each has 6. Okay, so now what do? Well, we have to at least link them up once. You have to at least hook them up once or it won't work, okay? So now what do you think I should do next? Well, this oxygen has 1 lone electron. This carbon still has another lone electron, so I'll hook those guys up. Now this guy has 1 lone electron and this guy has 1 lone electron. Now this is ugly, so I'm going to end up redrawing, okay? But this is a double bond, double bond. All right? What is important is the number of lone pairs on the central atom only right now. So there are none. There are no lone pairs on the central atom. Okay? If there's no lone pairs on the central atom, what does this look like to you? Hopefully it looks like a straight line. Like it looks like a shape, it looks like a straight line. So this is called linear. And now you're going to have to memorize all of these bond angles. Now, bond angle would mean from this bond to this bond, which is half of a circle, and a circle is 360. So what's half of 360? 180. So this is the bond angle for it. This is called a linear molecule with a bond angle of 180 degrees. Okay? Now, what they also will call this is like a generic type, AB2, where A stands for, oh, shoot, I'll go back. Where A stands for the central atom. A is the central atom, so that would be carbon. And B2 just means there are 2 things bonded to it. This is like a generic description of a molecule. All AB2 molecules will end up being determined as linear and having a bond angle of 180. So 2 atoms bonded, no lone pairs, 180. Okay? All right, so we're practicing now, right? Oops. I would like you to draw BH3. So I'm going to give you a second. Okay, so this is what you should get for BH3. Notice this is an incomplete octet. The boron only bonded 3 times, which means it only has 2, 4, 6 electrons around it, and it is stable like that. It is okay. Now, if I want to know what shape this is, I really have not drawn this proportional, meaning look at all this empty space up here. So this whole VSEPR theory is this idea that electrons don't like to be next to other electrons. Electrons repel each other. Oh, oops, sorry, it's VS. Okay, I wrote it wrong. Okay, valence shell electron pair repulsion. So like the electrons right here don't like to be next to these electrons, and these electrons don't like to be next to these electrons. So what they will do is they will orient themselves as far away from each other as possible in space. Well, look at all this empty space right here. So I'm going to redraw this to the best way where I can get them as far away from each other as I can. Okay, now this kind of looks like a triangle, right? Which is also 360 degrees. So this is a bond angle, this is a bond angle, and this is a bond angle. So it's a 360 split in 3 parts, right? Which is 120. And so this guy's name is trigonal planar. Trigonal planar is a compound that has 3 bonds attached to the atom, 0 lone pairs on the central atom, and its generic type is AB3, meaning there's a central atom A, that would be boron, and there's 1, 2, 3 things bonded to it. That's what the 3B stands for. And they call this trigonal planar. Trigonal because it looks like a triangle, planar because it lies flat in space. It lies all on one plane. Nothing is like sticking up or going out. It all lies flat in one plane. Okay, we're almost done for the day. So please draw methane. CH4's name is methane. So carbon has 4 valence electrons. Each hydrogen has 1. So I'm going to hook them all up. Now, the way I drew this, it looks like a plus sign. And I get that, and I understand that. But a plus sign would have 90-degree angles in between it. So the question is in 3 dimensions, right? Obviously this computer screen is flat. In 3 dimensions, can I orient this so that these electrons and these electrons and these electrons and these electrons are further away from each other? And that answer is yes. And it looks like this. It looks like a tripod with a camera coming off of it, okay? And it is called tetrahedral, and the reason it's called tetrahedral is because it has 4 faces. It's kind of hard to see on here. So 1 face, 2 face, the back face, and the upside down face. 3 on the top and then 1 underneath. Okay, tetra means 4, hedral means sides. All right. And what's interesting now is now our bond angles aren't 90. So our bond angles are 109.5, which is better than 90. That means I've spread these bonds as far away from each other as possible, and they're not repelling each other. So an AB4 molecule is an atom that has 4 things bonded to it with no lone pairs on the central atom. Okay. It's called tetrahedral because it has 4 faces. 4 faces. And its bond angle is 109.5. I highly recommend you making flashcards for these. All right, 2 more. I got 3 minutes before the bell rings. 2 more. So this is sometimes how they draw 3D modeling because, right, these molecules exist in 3 dimensions. So this is coming out at you. This would be going backwards. This would be like methane in 3 dimensions where we spread out the bonds as far away as each other as we can. Now, this molecule is kind of like it's kind of like methane except for, so there's nitrogen, and then here's my 3 hydrogens, except for having a bonded pair on top So right in methane, CH4, this was a bond. Now, instead of it being a bond, it's a lone pair of electrons. So they call this AB3, an atom bonded 3 times with a lone pair of electrons. Okay? Now, lone pairs repel bonding pairs more. So what happens is, since there's no atom coming up here, it pushes it down into a pyramid. It's not going to lay flat anymore, and it pushes it down to a pyramid, and they call it trigonal pyramidal. And the bond angle slightly changes from 109.5 to 107.5 because this electron pair actually repels these bonds more. So it looks like a pyramid. So this is more of a three-dimensional drawing right here. It looks like a pyramid, and the bond angles are 107.5, evenly around the bottom of the pyramid. Okay, one last one. Please bear with me. It's one you know very well. Water. Now, it is very common to want to draw water like this. So oxygen, hydrogen, hydrogen. And just please bear with me. I know if the bell rings, you can still hang out for a minute. You have 7 minutes to pass if you're in class. So there's the oxygen with 6 valence electrons. Here's the hydrogen. Okay, this is kind of ugly. I should have put this electron down here, right? And as at this point right now, this is probably how most of you will draw it, which is okay for right now. So this is a central atom, oxygen, bonded twice to the hydrogens with 2 lone pairs of electrons. Now, when you look at this, you probably want to call this linear, okay? But the thing is we work in 3 dimensions of space, meaning then these electrons are close to these electrons, and these electrons are close to these, and they don't want to be. So what really happens is those lone pairs of electrons bend the bonds, okay? And they create what's called a bent shape. It's bent, okay? The lone pairs bend it, which makes the, and remember, the more lone pairs you have on the central atom, the more it bends the bonds. So my bond angle shrinks even more, going from 107.5 to 104.5. Okay, so this is called bent. It also could be called angular because it looks like an angle. And this is because the lone pairs on top of the oxygen repel the bonds involved in the water molecule. It pushes them away. They want to move away from each other. Now, I know it's hard to see. I should have made this so I could draw on. I'll do it tomorrow. I know these electrons right here look like they're next to each other, but they really aren't. These electrons would be like on this side of the molecule and then again on the other side. So they really have spaced themselves out. On paper, it might not look that way, but remember, paper is flat and we're working with 3 dimensions. So there would be like these lone pair of electrons here and then also on the total other side of the water molecule. Okay? I haven't put your homework up for tonight. I did put the answer key up for last night's. It will be up. You will have homework tonight and tomorrow, so please check Canvas. You can head out now and be ready for another daily quiz on periodic trends and bonding on Thursday, please.